When you provide forecasts, especially when they are used for decisions, socioeconomic decisions, policies, strategies, and so on, you need to have metrics which measure the accuracy of the forecasts, and there are never unique metrics, but each metric tends to emphasize different thing. So here are the four most commonly used metrics. There are good papers on this that you can read up. The root mean square is the easiest one for the ensemble mean forecast. It provides information on how close on average the mean of the ensemble PDF is to the observed state. So remember the observed state, when you observe any particular thing like a 2-meter temperature on a given day or a given week or a month over a region over many years, it has a distribution of probability. So probability density function can be computed, and as we talked about before, you can think of the initialization circle of the ensemble members as the probabilistic distribution in the start of the forecast, and then the ensemble members end up in a bigger circle, diverge over forecasts, as we saw before. Maybe here. This is the around the this is the forecasted probability distribution function, which has to be as close as possible to the estimated observed PDF. Right, that's the goal. And the measure RMSE is basically looking at the mean ensemble PDF distance from the observed state. Okay, it's the simplest one to do always, and RMSE is a very common acronym that you hear all the time. The Brier score measures the correspondence between the forecast probabilities. Remember, ensemble forecasts are always probabilistic forecasts as opposed to just single realization, which tends to be called deterministic forecast. And observed frequencies for specific events. So Brier score is the distance from that diagonal that we saw, such as the probability that the 2-meter temperature anomaly will exceed 4 degrees centigrade in this case. Okay, so anomaly is what you are always trying to predict. If there is zero anomaly, then often you don't get any credit for it. It's like just persisting, right? The area under this is ROC, the area under a relative operating characteristic curve or ROC curve. It measures the capacity of a probabilistic system to discriminate between the occurrence and non-occurrence of events. So it's let's say a snowstorm is coming. Is it going to occur or not occur? So there is, of course, how much snow and so on, but these are events. A heat wave, is it coming or not coming? So the definition of a heat wave with respect to the climatology of that place has to be in place, which is the observed state. And the continuous ranked probability score that we saw, CRPS, measures the average distance between the forecast PDF and the observation, i.e. a narrow distribution centered on the observed value, not the observed PDF, and with a width that represents the observation uncertainty. So you have observed value and observation uncertainty. Okay, so when we do forecast data simulations and so on, when we are merging data with models to initialized, we have to always carry these observational error covariances, observational uncertainties, mapping observations onto the model space, and so on and so forth, including model error covariances, model uncertainties, etc. So this CRPS score is the equivalent of the RMSE, which is often used to evaluate single forecasts for probabilistic forecasts. Okay, so that just means that the each ensemble member from the ensemble mean, for example. Okay, hit rate. So this is the ROC curve for the ECMWF seasonal S4 prediction system of 2-meter temperature anomalies in the lower tercile in A and C, and the upper tercile and this is for the tropics, and this is again for Europe. Okay, so diagram refers to the, again, 2 to 4 month forecasts started on November 1 and valid for December, January, February. So you are starting on November 1. It's 2 months for December, so November, December. January will be 3 months, November, December, January, and February will be a 4 month forecast, so November, December, January into February. That's how you think about it. Okay, so here again, this is confirming what we saw before, that the tropics have higher skill than for Europe for the 2 meter temperature forecast at 2 to 4 month lead times. So the ROC area in A and C are 0.820 in both cases, and 0.570 and 0.540 here. And you can see that this is above, this is below, but it doesn't matter. You are looking at false alarm rate and hit rate, which means prediction is accurate versus prediction is giving you a false event occurrence rate. So larger the area, the better the ROC score, more reliable is the ensemble forecast. So this is similar to the CRPS, which is a RMS error measure, but this is similar to the reliability score that we looked at before, or the Breyer skill score in terms of the deviation, where the axes are different. There you had observed probability and forecast. Okay, so the other one is to look at cost benefit, cost loss ratios to estimate potential economic value of the forecast. Here you take an event and the users determine the loss they would face if the event occurred and the cost they are willing to incur to protect against this event based on the forecast. Okay, so we are not going into details on that, but that gives you a sense of the potential economic value of the forecast. Okay, so here is PEV of the ECMWF single high resolution forecasts in blue lines, and we are comparing them against the ensemble based probabilistic forecasts in the red line, and the CL ratios ranging from 0 to 1. So cost loss ratios are here on 0 to 1, and for four different forecasts: 2 meter temperature cold anomaly lower than 4 degrees in A, 2 meter temperature warmer than 4 degrees in B, 10 meter wind speed stronger than 10, and total precipitation larger than 1 millimeter per day. So PEV average values have been computed considering ECMWF operational forecasts for October, November, December of 2016, verified against synoptic surface observations, or SYNOP as they are called. Okay, so this basically shows you that, I think it's reversed here, blue lines are the ensemble and the single high resolution forecast is the red line. So the main message is that the potential economic value and the cost to loss ratio is better for ensemble forecast system for all of them, for the 2 meter temperature anomaly of lower than 4 degrees centigrade, higher than 4 degrees centigrade, 10 meter wind being stronger than 10 meters per second, total precipitation being larger than 1 millimeter. So even in terms of applicability or use of the forecasts, ensembles, probabilistic information provided by ensembles have higher value. So they have higher skill score, and they also have a higher value for users when you look at the cost and loss ratios. Okay, so that gives you a sense that we have all the reason to rely on ensemble forecasting and issue probabilistic information. There are various ways in which done. The International Research Institute for Climate and Society at Columbia, for example, gives quartiles. What is the probability in quartiles that a deficit season is coming up in terms of rainfall, or warm season is coming up, and so on and so forth. Okay, so oftentimes they have to be developed together with users consulting what they like, what kind of depiction they want.